Alright, here is the answer key for the second practice test. I'll go fairly quickly, so you're going to have to pause if you want to hear things a second time. All of the named quadrilaterals that have exactly two lines of symmetry, this exactly thing is an important word. Symmetry is a word we've talked about, so you're applying that concept. The only two that have exactly two lines of symmetry are the kite, because you've got a line of symmetry. Whoa, the line of symmetry is there. I take that back. The rhombus, it's a rhombus because you need to have another line of symmetry this way. So it's a rhombus, and then also a rectangle. Rectangles have a line of symmetry there and a line of symmetry there. So rhombus and rectangle. Only two. Check out the others and you'll see they do not work. Analytic geometry is the application of figures on the coordinate plane. So I'm just going to abbreviate that. You can coordinate plane, and you can remember René Descartes' invention, René's idea. Alright? All of the named quadrilaterals with congruent diagonals, just the isosceles trapezoid, this line is going to be the same as that line, and then the rectangle, congruent diagonals. Alright? So isosceles trap and rectangle. Then inclusive definition for a trapezoid. We would say that a parallelogram has two, so it is always a trapezoid if we're inclusive. Every single time we have a parallelogram we have one or more, so that's an always. You use the converse of AIA to show two lines are parallel, okay? Two lines are parallel. Fill in the blanks with the coordinates for the remaining two vertices. Whoops, I guess that should say 3 vertices, so that's a bit of a typo there, of the kite below, with the lengths, sides of lengths 13 and 20. Well, if this is 20, that's going to be a right angle. If this we know goes out 12, then we can do Pythagoras, that's a right angle, that's going to be 5. So this is left and right 0, then minus 5. This is going to be 12 this way, so this is going to be minus 12 and 0. And then this one is at 12 and then 16, 20. That's a 3, 4, 5 triangle that's been multiplied by 4. So this is going to be left and right 0 and up 16. Okay, so you're just going to want to do the 13 squared equals 12 squared plus, and then this would be like x, y, the y value squared, and you'd solve and you'd see that y equals 5 down there. Alright? Prove that the diagonals of a square are perpendicular. Another little typo. Okay, I have gone to a larger sheet of paper to show the two different ways to do number 7. I sort of gave you very little room there because I was trying to save paper. But there are many ways to do it. Please bring in your version and I can tell you how close you are. You could certainly draw diagonals and you could get to congruent triangles and you could go multiple steps through that. That would be okay. I think this is the most straightforward, and hopefully you'll realize that this is all legal considering we're applying the properties you're supposed to know. Step number 1, I'm saying that ABCD is a square. That's given. Step number 2, and you could do this in one big step, say that all the sides are equal to each other, because that's the definition of a square. But I just separated opposite sides as a pair to say that they're equal, because once you've got opposite sides equal, and you've stated that formally, then you can say that this shape is also a parallelogram. That's the converse property of a parallelogram. We have our properties, and they work sometimes forwards and backwards. You should be starring those and noting which of the properties work that way in converse and original form. Then we say that the diagonals bisect each other because that's a property of this thing we've now proven to be a parallelogram. So we're going that way with it. Then we can say, well, adjacent sides, consecutive sides are congruent. That's also the definition of a square. And then once we have consecutive sides, we know it's a kite. And once we know it's a kite, we know the diagonals are perpendicular because that's the property of a kite. Okay, so once again, we're applying those definitions and properties. Another way to do this would be as a coordinate proof. I'm just putting a square down. I'm giving its coordinates at the origin here 1, and then at over A, up and down 0, over 0, up A, and then this corner point would be A, comma A. And then I put in a couple of extra steps here to show that the diagonals are the same length. I decided later that that's not really necessary. You can pretty much start by just saying that, hey, that midpoint for each of these segments is the same. When you do the math of the midpoint formula, it's the point 1/2 A, comma 1/2 A. That's both midpoints. Midpoints. And then you want to say that they're perpendicular, and then I show that the slopes for AC is negative A over positive A. That's the rise, negative A, and the run of A. Well, that's negative 1. The other slope, by the same token, is positive 1. They're negative reciprocals, so they are perpendicular, and they're bisectors. Okay. Then for number 8, this is the one that had the typo. I corrected this, so this is positive 3. I've done the math. This is where I discovered the typo when I was filming before. So I'm just going to pick up from there, just again to save time. If you go the arrow method, from the y value first, from 6 to 27, that's a rise of 21. From negative 20 to positive 22, that's a run of 42. So I just have that first slope there for AB, and that's 1/2. Well, that turns out to be the same as the slope from C to D. It's the same exact numbers, down 21, back 42. So these slopes are the same. Here's where the typo was, though, from let's see, from D to A, from 3 to 20. I like writing this second point over here. Here's A repeated, just makes it easier. From a negative 35 to positive 6, that's a rise of 41. From positive 3 to negative 20, that is a change of 23. So these are not perpendicular, but they are the same length, and they are their own same slope, 23 here. So 41 over 23 and 41 over 23. So these guys are parallel. So this is in fact a parallelogram. Parallelograms have opposite sides that are at the same slope. So that's parallel to that. And then what I want to do is show a property of their diagonals. So this diagonal is going to cut this diagonal in half. And so I just need to show that the midpoints are the same. So I'll do midpoint of AC. So I take the A and the C coordinate and I add the x's. That's negative 20 for the x plus 45, and I'm going to divide that by 2, and then I'm going to do 6 minus 14. 6 plus a negative 14 is 6 minus 14 over 2, and this equals, well, that's 25 divided by 2 is 12.5, comma, and that's going to be a negative 8 divided by 2 is negative 4. And then I think you'll see that when you do BD and you do the midpoint there, it'll work out to be exactly the same. Okay, so I think I'm running out of time, so I'll let you do that math, but check that out. Then prove that it is impossible for one of the base angles of an isosceles triangle. So that's an isosceles triangle. I'm trying to prove that this angle here cannot be obtuse. Well, that looks pretty obvious, but I prove that using a proof by contradiction. So I'm just going to save time by saying, whoops, put this down here. I'm going to say it is impossible. I'm going to assume the opposite in step 2. Assume and state what it is. An isosceles triangle has two base angles greater than 90 degrees. Alright, well, step 3 is pretty easy then. You can call that A and B and C. Angle A plus angle C is greater than 180 degrees, but triangle sum equals 180 degrees. Actually, I think I just hastily went over something. I said in one angle. So I do need to say that assume that an isosceles triangle has one base angle. And then what I'm actually saying is angle A is congruent to angle C. That's base angle property of isosceles triangle. I'm going too fast here, sorry. But you're saying that, hey, if this is an isosceles triangle, these angles must be equal. If they are equal, then I have two angles that are greater than 90. So if I add them up, they're greater than 180 degrees. But that's the contradiction. Triangle sum is 180. So that is a problem. So step number 2 is false. It's been contradicted. So step number 1 is proven. All right? And again, I could write that out longer, but I don't have time. All right, hopefully that's enough to get you going. Good luck.